label for the domain.
Okay, that's from your learning by
So this is the bisection.
Yeah, okay.
Yeah, it's the more uniform
Wow,
partition.
even in 2 dimensions, is this complicated?
Yes.
Oh.
So then.
Is it possible to use some like, I mean, what we learned actually, card? I mean, so like,
Card.
Yeah.
Yeah.
I mean,
So card is a card is a kind
It's
of
basically
this is a kind of card. Yeah, but we are using some different direction of the partitions.
so you
the
do
card
have a
is-
lot of observations. This is good.
Yes.
We usually don't have this many. Yeah.
So typically, if you look at the satellite data, so that is the already millions, right?
Yes,
And then,
yeah.
so if you putting the
Oh yeah, that's a
time,
very good application. Yeah.
so if you have a
I see.
time domain, then you have
Yeah.
some maybe gigabyte data, and then so terabyte data. So anyway, what I did is here is we have some prediction from so from the left side of the domain, and then so we have the right side domain. We have the prediction. So we look at how those two predictions are converged with the number of pseudo data is increased. So this is the B, is actually the local GP. It's good actually, but the blue line is actually one prediction, and from the right side, and this yellow, the red line is the prediction from the left side of the boundary. Okay. As you can see, except a few positions, the prediction is the pretty good match already. Okay. But there are some mismatch in some points, okay? Especially in some this kind of the peak points, the difference is large. Okay? So that's actually the pure local GP because the pseudo data is the 0. Okay. But if we increase the pseudo data, it's just 3 points per boundary, and we have more the converged output. And as you can see, the converged output is really close to the exact GP. And if you put the 5 in that's almost consistent. Okay, it's the two predictions is almost consistent to each other. Okay? So if the process is very smooth, anyway, so what I mean is this. Okay, just a few number of the pseudo data, you can match the two processes very closely. So this is the more comprehensive simulation data. Okay, we generate the GP. Okay, and then so in the general dimension. We change the dimension from the 2 to the 1 to the 100. Okay, so we test it up to the 100 dimension. That's sufficient for the my purpose. Okay, and we have the square exponential functions. Okay, and then so we fix actually the intensity, but we have the scale this range of the covariance parameter is change it for testing how our method is performing for the different covariance ranges. Okay. So each data set, okay, and we sampled the 10,000 locations of the X, and we sampled the actual Gaussian process observation from the disk covariance. Okay? And then after that, we added some Y norms. Okay? Variance is the 1.
Even here is 100. When you do the partitioning, it's going to be really
is the max, right? And
yeah, it's not going to be connected regions like boundary points. You know? That's going to be really difficult.
Yeah, really difficult, but we showed actually at least this idea is working up to the 100 dimension. But the computation is really so messy because we need to have the.
I'm not even worried about the computational part. I'm worried about actually the prediction. I mean, the
accuracy is pretty good, but still it's a large, like 100 dimension regression is not easy problem.
yeah.
And then so if you use any other method in the general regression without any partitioning, and then performance is not good.
So this 10,000 observations is enough in this situation?
Yeah, for this one is actually the kind of we got the good result because the covariance field is kind of smooth.
Okay.
So as you can see, this is it's square exponentials, right?
Mm-hmm.
So variations is not like a big jumps, right? But still we control the low and for making the jumps like this. Okay. So if we low is the 0.1, then making very low the sample functions. Okay. And then if you have some increase, that's the medium covariance range. We have the kind of sample point is like this. Okay. That's the 1D examples. Okay. If you put the very long range, function is the very smooth with some noise, right? So we tested actually the algorithm with a different choice of the tuning parameter for each case. Okay? And we replicated experiments, 25 cases for removing, so kind of relieving some of the random effects, okay, in the experiments. So what we collected is that we have the interior mean square errors. We take the boundary mean square errors to see how our method is working around the boundary predictions, also in the interior local region predictions. So this is the kind of the result. So we have the many the raw data, but this is just the summary data, and then so just illustrating some of the outcomes. Okay. So this is the depending on the covariance range. This is the interior mean square errors. This is the boundary mean square errors. Okay. So basically, this implies prediction accuracy within the local region. This is the implied prediction accuracy around the interior boundary. Okay. So we tested the short range, mid range, long range covariance. Okay, as you can see, this is the log scale anyway, and then so because the range of the MSE is pretty large. So the range of the data is the in between the -10 to the +10. Okay, so that's the original range of the data in the response. But the MSE is for the short range is the still, I believe it's reasonable, given that the range of data. But this is quite large compared to the mid and long range. Okay? So if the data is at least smooth, and then so our approximation is very close. This is the mean square error is the difference between the hours and then so full GP, okay, exact GP. Okay? So we got the exact data from the full GP and compare with our prediction with the full GP. Okay? So mean square error is pretty getting small. It's the 0.001. And if the range of the covariance is the mid and long scale range, okay? And then so that is the kind of improve if you are putting the more boundary point pseudo data, okay? Then we have the improvements, but that is the kind of saturated after the 5 or 6. Okay? So this boundary MSE is also similar pattern, but so difference is a little higher than the interior MSE. That's the kind of natural because boundary the prediction is the poorer, and but still is the so long range and the mid range. We have the MSE difference around the boundary is still less than 0.01. Okay? It's pretty close to the full GP. So that's the actually effect of the covariance range. Okay. So we expect actually that this method is the more reasonably working in the functional space is the smoother. It's not rough like this. Okay. If the data is rough like this, and then so we try the other state of art. So those are state of art also does not working very well.
Unless we have a lot of observations.
Right. Right. So this is actually some effect of the tuning parameters. Okay, we have the two tuning parameters. First one is the number of partitions. Okay, and then so we fix how we partition. So the tuning parameter is the number of partitions, and the other is the pseudo data per each boundary. Okay, so this is the actually combined result. Okay, so you have the this one is actually somewhat. So I created today actually, and then this is the kind of so like a typo, and then this is the mislabel. Actually, this is the 4 lines, right? And then so this actually legend is wrong. Okay, so this the green line is the partition 16 case, and then blue line is the partition 32, and then so we increase by the so multiply by 2, 16, 32, 64, 128. And this is the outcome. Okay? So as you can see, the K is actually increasing. So your outcome is the something MSE. Okay, MSE is the.
So you have a really large K. Shouldn't I may be able to reduce the number of B?
So number of B is actually the effect is the pretty negligible after certain points, right? And then so
yeah, but for example, K 64 or K equal to 128.
Mm-hmm.
If I have K equal to 128, I can possibly reduce B, right, in your setup to get the same MSE.
Sure.
I can't really see it very well, actually.
So you can see it's the K 128 is the data is the much faster converge, right? And then so then it's the. So with a small number of bits, the more you have the accurate result than just the large partition. For the large partition, you need the more number of the pseudo data. But anyway, the pseudo data is the number of pseudo data. Sure, is the like you mentioned, depending on the choice of the K. But with some certain choice, what we can observe is anyway the result is the kind of so kind of converge to the very similar, and then so that is the MSE range, and as you can see, it's the range of the MSE is pretty small, and then depending on
Why
which
the
person.
MSE goes up?
Yeah, that one is actually I'm kind of. So the K is the 128. If you are putting the more B, and then so a slight increase is there, and then this might be some numerical issue, I believe. But I'm not sure exactly, but this bouncing up is some related with the numerical issues.
It might affect.
So because actually the K is the 120, right? And that's your observations is the much less than the pseudo data,
influence
right?
of observations.
Right.
But that's not only computation easier to me.
Yeah, it's not the computation.
Yeah.
But if you have a very large partitions, and then so pseudo data is the kind of
It becomes
it's a
more
dominating,
dominant,
right?
yes,
Yes,
exactly.
more dominating, and then so
Yeah.
surely there are some negative effects, right? Yes. So then it's the B's cannot be very large, and surely it's the less than the training data. Yeah. So this is the computation time, and then so computation is the more dominant depending on the dimensions. But if the dimension is less than 10, and then so computation is not much different. Okay? And then so but the dimension is the 100, and then so you need the more pseudo data, and then so accordingly you have the more increased computation. So then the suggestion is the K and B is the something like that. It's just the empirical suggestion, and the K is the more like chosen. It's in the range of the n divided by K is around 200 and 600, which means each local region good performance is coming from the data size in the local region is the 200 to the 600. So if you have a bigger data, you surely have the bigger K. Okay? And the surely the case cannot be very large. If the case is too large, and each local region have the very small number of data, and the local prediction is getting poorer, and then just matching does not solve the problems. And also B's cannot be very large, and then so our suggestion is that depending on the D and B, and then so that should be 15 and 400, and then that balancing the computation of the two parts of the inversions. So we compare with actually some state of art, and then we chose the one representative from each category I reviewed. The PGP is actually my last version of it's a very similar approach, but the modeling is different. And this is what I present today is the newer version. And then Markov random field approximation is used as the representative of the sparse approximation. And then so Bayesian committing machine is the representative of the mixture of the local Gaussian GP. And the PIC is the representative of the low-rank approximation. And we use the 5 data set, but we only present these 3 representing examples. One is this is remote sensing data, satellite. And then data size is around 200,000. Dimension is 2. And the Sarcos data is the manufacturing data from the robotics. And the dimension is the 21. Data point is the 44,000. In the flight data, that's the service, flight service data, and the flight day data actually. Okay? And the dimension is the A. And then so number of data is 800,000.
In some scenarios, Gaussian process may not be a good tool, right?
Yes.
I mean,
Yeah, but those are Sarcos, and then so remote sensing is the kind of popular example of the
the
Gaussian.
first one is okay, actually, I agree.
Yeah.
But for flight delay,
Yeah, this one is used in one of the literature I read in the Gaussian process. It's just one test data set, so we're not sure.
outliers, I mean, not necessarily.
So maybe
As far as I know.
many outliers, I believe. Is there.
Okay.
Yes, many outliers. Maybe enter data is maybe corrupted. Yeah. So this is the performance criterion. MSE, NLPD. The MSE is the kind of the tested error of the estimated posterior means. NLPD is the kind of negative log likelihood to the test data. So if you have the predictive distribution, posterior distribution, how this posterior distribution is relative to the test data, that's the meaning of the NLPD. Both value is the smaller is the better. Okay. So this is the TCO, is the remote sensing data. So we compare the PIC, PGP, and our method first, and with the squared exponential functions, because the other two methods does not work with the So scale exponential. For example, in the Gaussian Markov random field approach is that there are actual computation for the square exponential covariance function. Precision matrix is pretty dense actually. So then that was not very working well for the square exponential. So then we compared only 3 for this square exponential model. But the other 2 is that we compare with the exponential covariance model. So as you can see, this is the MSC. Ours is pretty comparable with our previous version, but outperforming the PIC. Okay, that's the low-rank approximation. This is the computation time span, and then this is the corresponding MSC. And then but if you look at the NLPD data fitting, and ours is outperforming the other 2, which means mean prediction is the comparable in between the PGP and our method. Okay, but our predictive variance estimation is the more closer to the more better fit to the best data set. Okay, so then our predictive variance is the more so representing the data distributions. Okay, so we are capturing the uncertainty of the test data the more accurately. Okay. So this is the exponential covariance model. We compare with the Gaussian Markov random field, and then the one is the computation time is much higher. Then it's not actually comparable, but we compare with the PGP, and then that is actually pretty similar to the square exponential model. So the mean prediction is similar, but NLPD is the likelihood fitting to the test data. Okay, and ours is much better. So Sarko's data, and then we see some mean prediction and NLPD. This is the log scales. Okay, actually the difference is not that large, but the PIC is the variance depending on the choice of the tuning parameter is very large. Okay. But ours is pretty consistent around this, but the best case comparison is the PIC is much better in the MSC, and then. I mean, Sarko's is the 21 dimension. It's the high dimensional case. I believe ours is not that competitive in the high dimensional case, in the 21 dimensions. And then, but the NLPD is still ours better, but the PIC is some numerical issue. And then predictive variance is going to negative because of numerical issue. And so we cannot actually compute NLPD for the PIC. So because of we do not have any variance. So then the PIC has the accurate prediction in the MSC in the best case, but some numerical issues. So that is kind of explaining some limitation of the PIC. So this is the flight data. The flight data is the data size is too large, and we only tested for the limited configurations. And then number of the pseudo data per boundary is 5 fixed, and the PIC is we change the number of latent variable to the 1000 to the 1500, and then for making the computation time is comparable to each other. Okay, and computation is this one is much faster, and then MSC is ours is the better. Okay, and then the flight data is so I believe this should be comparable. But let me double check. And then so I remember the computation is comparable each other, and then MSC is ours better. But here is something weird is. So anyway, basically the flight data is the MSC is ours better, but the computation is let me double check. So just the discussion about the real examples, and the benefit of our approach is when the similar time is invested, MSC is outperforming, and the word similar. Okay, most of cases ours is much better. But our previous version, mean prediction is comparable, right? And then to this new version, okay? And the NLPD is ours is outperforming all others and all the cases. The reason why that is ours is the better generalized uncertainty. Is that we quantify the uncertainty of the prediction is much better because our Poisson distribution is the better fit to the test data set. Okay? So to see the reason why, and we kind of computed some of the quantiles of the test data set belong to the range of the variance predicted. Okay. So suppose each method has the mean prediction and then posterior variance, and then we count the test data set within this range and with the different C values. Okay. That kind of giving some percentage of test data within the range. Okay. And then also we get the ground truth data from the normal tables. Okay. So with the range of the C, and that's what is the percentage of data belonging to that range, and then we can easily achieve from the normal tables, right? And then so this is the ground truth, and for the different choice of the range constant C, and then so ours is the kind of is the closer to the every case. But if you look at the whole other case, PGP, that's our previous version, seems like this PGP is kind of overestimating the predictive variance. So with the only 0.5 of C, and then test data point 70% is included, but that should be only the 38%. But the PIC and the RBCM, if you look at that, is that their percentage for the small c is the pretty small. So compared to the ground truth, which means their predictive variance is the too narrow. So they do not actually quantify the predictive variance very closely. Okay? But ours is the older case is very close to the real percentiles. So that is the explaining the why our method is the outperforming the NLPD, how we the quantifying the uncertainty in the test data set. So that's the pretty much of the discussion of the real data. Yeah, that's the end of my presentation. So sorry for the many typos. I just created the slides yesterday.
We're typo tolerant.
Yeah.
We have so many typos in the presentation. It's very clear, very impressive. Any questions? I hope everyone here can gain more knowledge in based in prior computation, number measure. This should be in our department. You should talk with small in fact in computation of Bayes in this case.
Yeah, I was in your presentation last semester as well, I think. But I think the method is totally different from your last presentation.
Yeah, the approach is totally different. And so last year is what I did is we have the local model. How we patching is we have some optimization problems for minimizing the difference.
Yeah.
But that causing problem because we cannot derive the actually likelihood function for hyperplan.
You mentioned that.
Yeah.
Oh. Okay, but if you use this prior, you can still show the final.
Yes.
Any more questions? Okay, thank you all for coming. Thank you.
Thank you.
Let's end the part again.
Yeah, sure. So you have some interesting idea.